Thank you, first of all, for organizing and inviting me for this day. I'm very pleased to be here with the Guru of Computer Science. So I cannot say that I'm within the static analysis community or abstract interpretation community. This talk is a bit different, let's say. We'll talk about strings and constraint solving, but at a very high level. So basically, what we have done in the last years. Well, no need to describe what strings are. Very well known, use data type, both to encode, represent input and output data, but also used to evaluate the code dynamically. So probably because of some cybersecurity issues, over the last year there has been active and growing interest in string analysis from both static and dynamic perspective. So for the static string analysis point of view, we basically over-approximate computation involving strings. And this has been done very well by the Venice group. So there are different abstract domains that can be used to represent a set of concrete strings. So we can keep track of the length. The character inclusion basically means the set of characters possibly occurring in a string, or we might take care of the prefix or the suffix, the known prefix or suffix or a string, or we might do something more complicated like automata basis. And actually, I just read that there is a proposal on relational string domains. I haven't read the paper, but I guess it would be very interesting to understand how this is work, while the domains are not relational. On the other hand, if we use the dynamic approach, we under-approximate the set of possible runtime states, possible computation involving strings. So for instance, we can do a symbolic or dynamic symbolic execution, also known as a concolic execution of program containing strings. So basically it becomes a reachability problem. So while we execute the problem concretely or symbolically, we collect path conditions, so constraints that lead to a particular path being taken during the execution. So basically a path is feasible if the corresponding path condition is feasible. So what we need is actually a constraint solver, and if the computation involves strings, we need a string constraint solver. So what we've been doing last year is basically solving a constraint with strings. So we need to fix an alphabet, of course, and we might have, say, well-known constraints like concatenation of constants and variable. Yes?
Excuse me, before you continue, you said that we need not go into what is a string, but one thing is important. Can you override the terminator in the language you are considering?
Oh, no. Just like,
Okay, so they are not systems.
Yeah. So more abstract level. I over-approximated my explanation. No. So we are dealing with finite strings. We need to fix an alphabet, and typically we also fix an upper bound on the maximum string length. Even though this is not really necessary, but typically we do. So we can have length constraint, we can have the constraint saying that a particular string variable belongs to the length denoted by a regular expression, and also more complex constraint like replace or replace solve. So basically we can classify into three categories, like unbounded length string. I mean, concerned to the research in string solving being done so far. Otherwise, we basically fix an upper bound lambda, and we consider all the strings in the alphabet, which length is less or equal than lambda. Otherwise, we also, in the simplest case, consider fixed length string, where actually all the strings has a fixed length. So the theory of string constraint solver, the foundation, dates back in the 40s at least, with the central concept is the word equation concept. So we have basically string variables and constants, and we try to solve the equation, meaning that we try to assign to each variable a string value, constant value, making this equation true. So McCann in the 70s proved that if we don't have quantifiers, this theory is decidable. I read that Plandowski, I don't know how to pronounce his Polish name, said that this is one of the most difficult proof he ever seen, so I trust him. I have an idea how this is true. I read that it uses this lemma, called Levy's lemma or Sunisian transformation, that is also used by string solver, at least SMT string solvers, to actually solve a word equation. So, of course, in general, we may have the stability issues. For instance, the general theory of word equation with length function is still an open problem. And what we can say is that modern string solving approaches nowadays can be grouped basically into three main categories. The one that are based on automata, the one that are based on word equation, and the unfolding based or reducing based approaches. So automata based are basically approaches where the string variable, the domains and the operation are mapped to automata operation. So we can use deterministic, non-deterministic, symbolic automata. So this is, of course, a well-studied theory and the core of many constraint solving theories. Of course, with this formalism, we can naturally handle unbounded-like strings. The point is we might have some efficiency issues due to the state explosion when we apply automata operation, and also if, depending, of course, on the type of automata that we use, we may have a problem with expressiveness. Of course, if they have a DFA or an ONFA, we cannot encode more complex constraint, denoting, for instance, context-free language or not context-free language. Sorry. While the word-based approaches are the approaches that are handled by, let's say, basically all the SNT solvers, so they natively handle the theory of word equations, plus possibly other theories like linear arithmetic or regular expression. So they rely on decision procedures, so algebraic results over the theory of strings, with, possibly extended with other operations. So they are more, let's say, expressive for sure and flexible than pure automata-based approaches. They don't have these, in general, these state explosion problems, and they can also handle unbounded-like strings, so we don't need necessarily to put an upper bound on the length of the strings. One thing, of course, they have to rely on, typically on an underlying SNT solver. One thing that we realized during our experiments, but this might be that because they are still at an early stage in their evolution, they are not still not very efficient, is that doing experiment, we realized that they have some scalability issues with very long strings. So when we use strings of 1,000, 2,000, 5K of characters, they don't scale very well, at least so far. This might be due to the case reasoning of SNT solving, or maybe might be just some initial implementation issues. And then another natural approach is that, okay, we have a string and we unfold into a sequence of characters or a sequence of something, a type T. So we might do a bit blasting, we might reduce to big vector, we might reduce to integer vectors, mapping each character to a number, basically, with a spatial configuration, maybe for empty characters for doing some padding, or maybe we can use a more symbolic approach. This can, at least according to our experiment, can be better to deal with long fixed strings, but of course we need to fix an upper bound. This cannot be applied for unbounded like strings. And also, we may have problem to prove the unfeasibility, especially if we use this approach with CP solvers as we've done, because what we have done from a technical point of view was instead of doing a pure, let's say, approach, unfolding a string into a number of characters, maybe padding with an extra symbol to say empty character, we do in a way a lazy unfolding. So we took inspiration from the bricks extra domain that was introduced in a paper by the Venice group, and we decided to represent the domain of a string variable in a constraint programming solving context as a sequence of blocks. So each block of this string that is called dash string, that we call dash strings, is a set of characters in a given alphabet with a cardinality, let's say, a lower and an upper bound of how many characters they might appear in their in the set denoted by this dash string. So for instance, in this example, we have either B or C followed by 0 to 1A and then 1 to 2 C's. Okay, so the set of concrete string denoted by the dash string is that one. So we use this abstraction and implement it in a constraint programming solver, which is a G-code solver, and it provided some good results. So according to the CP paradigm, we needed to define some propagators, so some, let's say, operation trying to narrow the domain of the dash strings until it get eventually fixed to a concrete value. So for instance, that dash strings B11, A11, C22 actually means the concrete string BACC. And these propagators, these algorithms were basically matched on the concept, based on the concept of dash string equations. So basically we matched two dash strings blockwise, and we try to determine where a block can match another block in the other string, in the earliest position, the latest position, and according to this position, we refine each block. So this is just an overview of some string approach in the literature. Of course, hybrid approach exists. So for instance, this Z3S3R3RE solver uses both bit vectors for bounded length string variables, word equation for unbounded length, and automata is an automated base approach for regular expression. Or for instance, the, let's say, evolution, the next solver as a Z3 saga use algorithm selections to try to predict which is the best strategy for a given problem. So in general, say that we can identify four main challenges for the future of string solving. Of course, we can extend this approach for more complex, more exotic string constraint, like back references or regular pattern matching or some kind of transducers. One thing that would be very interesting is try to introduce the closed learning approach to the string solving, because what we have done is not related to lazy closed generation. So modern constraint programming solver uses so-called lazy closed generation, meaning that they use some subclause to learn from the failures. While we are using say, pure finite domain solver like G-code, so we don't learn about our failures, and this might be bad, especially if we need to prove the unsatisfiability of a problem. Also, will be interesting to combine the static and dynamic string analysis, given that there is also good research on static string analysis, and actually use the technology we are developing for a real-life application like software verification, cybersecurity. Okay. That's it.
Thank you, Roberto. There are questions? Of course.
It's, if you had your slide, we see, no, not this one, we don't, yeah, this one.
Yep.
You see the coefficients are constant. There was an analysis by Alain Dutch who was using a similar idea, but there was only one coefficient.
Yep.
And what he was doing is you initialize by a constant, and you replace the constant that change at each iteration by a symbol. Then you do one more iteration, and then you use a numerical abstraction of the recurrence, so you could solve the recurrence equation in the... Mm-hmm. You have tried this? No?
Well, actually, we do, like, these are not constants in the sense that we string, so the lower and the upper bound until we get this equal.
Yeah, but
because we are not doing the static part within the dynamic, so we want a solution.
That's very approximate. If you have a recurrence relation on the coefficient, it would be more precise, I think.
Yes, I'm not sure about the efficiency, like
maybe you can solve the recurrence equation like in the previous talk.
Yeah.
Or you can approximate with some numerical domain. Yeah. And if there is an invariant on the coefficient, it will give you some specific class. Okay, but I thought.
And this is also like a bounded coefficient, or in general,
No,
also
no,
like
not
star?
unbounded.
Yeah,
Yes,
yeah, yeah,
yes.
yeah.
Because having the bound is some other problem.
Yeah, yeah.
In fact, yeah. It can be that the analysis will determine that it is bounded by some other,
Yes.
on the number of iteration or thing like that. Okay, so it was not really a question, but
Was a suggestion.
we don't have the answer today. So.
Any other question? No? Thanks, Roberto.
Thank you.